Okay, welcome to the M-Cubed weekly seminar. Today we're very honored to have Professor Paul Markowski as our invited speaker. Paul is the distinguished professor and head of the Penn State's Department of Meteorology and Atmospheric Science. His research interests include all aspects of supercells and tornadoes, from state-of-the-art simulations and analyses, which you'll see some of which you'll see today, to field projects. He was the co-leader of the Vortex-2 project. He's been involved with getting your papers edited and reviewed. He was the chief editor of AMS's Journal of Weather and Forecasting, and currently indirectly is supervising us through his service on the UCAR Packer Committee. Paul's a highly decorated member of our research community. In addition to being a fellow of the AMS, he's received the AMS Meisinger Award, the National Weather Association's Fujita Award, and the European Severe Storm Lab's DOTSEC Award. To add to this slate of accomplishment, Paul is also the faculty partner for the men's golf team at Penn State. So to tee off the talk now, a new pathway for tornadogenesis exposed by numerical simulations of supercells in turbulent environments.
Well, thanks for the really nice introduction, Rich, and for the invitation and handling some of the logistics with the trip. This is work that really began in 2019. It has a lot of NCAR fingerprints all over it. I used George Bryan's model for starters. George and I were undergrads together at Penn State last century, a while ago. The original study that today's work is derived from, that was motivated by one of my Penn State colleagues, Fuqing Zhang, who also has NCAR roots. Ying Pan is another one I've been working with on this. Also an NCAR former ASP postdoc. I obviously talked to Rich quite a bit as well, and Morris even played a role in, although he maybe didn't know it until I mentioned it to him earlier today, in spawning this study. So the title is rather provocative. Naturally, extraordinary claims require extraordinary evidence. I'll get to that eventually, but I first wanted to quickly summarize what I take as the community's consensus about the basic aspects of tornado formation. So we'll put on our storm chasing hat. This is most certainly not what the weather conditions look like outside right now, but this is actually from not far from here in eastern Colorado. We're looking to the northwest. We obviously can see that the storm is rotating. You can see the striations in the updraft indicating a mesocyclone. There's wind shear in the environment. The wind at the surface is at our backs. The winds above the surface are coming out of the screen at us. And that shear implies that there's horizontal vorticity. So the black arrow here represents qualitatively the horizontal vorticity vector, and the magenta arrow gives the sense of the vorticity associated with that. And the storm sucks in parcels of air, and that vorticity gets reoriented. It's not unlike the spin of a football going from horizontal to vertical. And this is, when we see this spinning mothership in the sky, it's just the visual manifestation of lots of individual air parcels having their vorticity rearranged from horizontal to vertical and made visible by the condensation. So this is entirely consistent. It's just another way of showing what happens when a vortex-line is uplifted by an updraft. Helmholtz, following Helmholtz's theorem, predicted that if you've got an viscid barotropic flow, the vortex lines just simply go with the flow. They are deformed, tilted, rearranged like elastic strings. And we rely on that characteristic of vortex lines quite a bit in severe storms meteorology to explain what we see. All right, one issue though when it comes to making a tornado is that if you look at this closely, the vorticity actually doesn't become vertical until air has risen quite a distance above the ground. So what we've kind of taken to be a truth for decades is that rain and downdrafts are really important. So where it's kind of fuzzy on the right side of the image is where there's some rain falling. And some of the rain evaporates, of course. That produces negative buoyancy, and air sinks. So there's an airstream typically sucked into the storm from the front side, and as it is pulled into the front side of the storm, it descends owing to its negative buoyancy, kind of like what's shown here in the figure. And along that path, there's also a horizontal temperature gradient. So it's warm out of the screen where we're in the ambient environment. It's cooler into the screen where you're into the heavier rain and evaporation. And that horizontal temperature gradient generates horizontal vorticity baroclinically. So this is yet another source of rotation for the storm. But one key difference between the rotation along this airstream and the first one that we looked at is that these air parcels are sinking as they approach the updraft. And there's some gory details here that I don't have time to get into. It could be a whole nother hour-long talk about what happens very close to the ground here. But long story short, you can get vertical vorticity very close to the ground, like is shown here, which is different than this other airstream where the vorticity is only acquiring a vertical component once it's ascended some distance from the ground. So that's how you get rotation in a broad sense about a vertical axis very close to the ground. That's not quite a tornado just yet. You typically, that gets you to on the order of 10 to the minus 2 per second or so, which is about 100th of tornado strength. So we go the rest of the way through stretching of the vertical vorticity, which can happen very rapidly. This is just, in other words, conservation of angular momentum, how a figure skater spins faster. And what we've learned over the years from field observations that is if this air is too cold, this air's got to be pulled upward. And if it has excessive negative buoyancy, it's very difficult to have large vertical accelerations, which translates into weaker convergence of angular momentum, weaker vertical vorticity stretching. On the other hand, if there's really strong suction from above and the air is not excessively negatively buoyant, then the stretching is much larger. And this is how tornadogenesis tends to be facilitated. So a picture's worth 1,000 words, as they say. I guess a movie's worth 1,000 pictures. Here's a movie showing this, and it basically tells the tale that I just told in the schematics. You can see rain falling on the far right side here. Air's getting sucked out of the rain. This is one thing that's special about supercell storms relative to non-supercell thunderstorms is supercells can suck up some of their own evaporatively chilled outflow and process it back into their updrafts. Normally, thunderstorms feed off of warm inflow, and the outflow just undercuts the updrafts. But supercells can also suck in some of their own outflow, and you can see that right before your eye. Clouds coming out of the rain, this air is almost certainly negatively buoyant, and it gets sucked upward. And you can see it acquires pretty strong vertical vorticity as well. This didn't make a tornado, but it came pretty close. And one thing that people in my line of work have been looking at recently, maybe it doesn't affect how we forecast storms in particular, but it's maybe an academic question, is there an additional vorticity source here that I didn't talk about? I focused on pre-existing vorticity through the environmental shear. I focused on an additional source through temperature gradients in the storm, but an additional source within the storm could be accelerations of air above a rough surface. That's another source of potentially frictionally generated vorticity, which could play a role here. How that goes from being orthogonal to the flow to being aligned with the flow and looking at things in the storm's reference frame versus the ground reference frame. These are details that are beyond the scope of what I want to get into today, but I'll just say for now that this is something that people have been looking at in the last 5 to 8 years or so, and maybe more like 9 years. Okay, so what I've summarized, I said 10 minutes. Yeah, it's almost on the spot. This comes from really about a half a century's worth of observations, simulations, and theory. An outsized portion of this understanding comes from right here inside of the walls of NCAR. Sorry, Rich, that's the best photo of you I could find online. that is rich. So a lot of this work was really pioneering, the modeling work done here. I'm not sure where our field would be actually without the ability to perform those idealized simulations, which allow us to really turn one knob at a time and isolate cause and effect and the relationship between storm environments and what the storm does internally. But one of the big themes is that to get a tornado, and this is really about 40 years now, I'd say, of just almost taken as a given, that in the absence of any pre-existing vertical vorticity, you need some sort of a downdraft. So we've seen this in observations. These are data from the Vortex-2 experiment. The trajectories are all passing through the rain, and they're sinking as they approach the developing tornado. So this comes from really hard to get dual Doppler radar observations. Here on the right, the blue is where air is sinking. We always see downdrafts wrapping around the tornado. Sometimes you see an erosion of cloud wrapping around the tornado, known as a clear slot. Here's simulation evidence. These are trajectories feeding the incipient tornado. The black contour here is just the radar echo outline. So this is the hook echo here where I'm pointing. And you can see all these trajectories sink and then move along the ground and then erupt into the tornado. And if we ran these forward, they would eventually shoot back upward again as the overlying storm updraft sucks them upward. Here's an animation from the same simulation I just showed. This is, by the way, from Johannes Dahl down at Texas Tech. The color shading is the vertical vorticity component, basically just right above ground level. And the reason I wanted to show this to you is because all of the action is basically on the cool side of the gust front. There's a blue contour that's maybe hard to see here. That separates rain-cooled air on the left from ambient environmental air on the right. On the right, we call that inflow. On the left, we call that outflow. And the vertical vorticity in the inflow, it's essentially negligible or zero. And in the outflow, however, that's where we're generating vertical vorticity near the ground. And it tends to coagulate in some areas, and sometimes if a few other things go right, these develop into tornadoes. But all of the action is originating where air is sinking in the rain-cooled air. That's the takeaway there. So, summary of the key points and what I'd refer to as the community's understanding. Downdrafts are really key. Horizontal temperature gradients, or you could reword that as more generally horizontal buoyancy gradients, because the mass of precipitation also can contribute to horizontal buoyancy gradients. Those appear to be a key vorticity source, at least based on simulations. Observing horizontal buoyancy gradients in 3D, that's a lot harder. And many have viewed tornadogenesis in supercells as kind of like a Goldilocks problem. You need to have some sort of downdraft to get a tornado, but if the downdraft is excessively cold, then that can short circuit the process. It can become disruptive, and that's because the ability to make a tornado depends on the ability to contract angular momentum to a small radius, and all the angular momentum about a vertical axis is on the cool side of that gust front. So you've got to be able to suck up air that has some negative buoyancy. But if it's too negatively buoyant, that's no good. So it's a bit of a Goldilocks problem. It can't be too hot, it can't be too cold, it's got to be just right. And then, as I mentioned, surface drag might be an additional vorticity source. There's some simulations that show this is maybe important leading up to tornado formation. Other simulations, it's not important until after the vortex is already established. There are, without getting into a lot of the weeds, some of the simulations are most certainly not all that realistic, especially some of my own. There's a Markowski reference here. These were highly idealized without even any precipitation. So that's, I'll make sure that as I cast stones from inside the glass house, I throw a stone at myself first. So I think that the jury is still out on this one. I think that's probably the most scientifically responsible answer. All right, well, we can, of course, critique this summary. One shortcoming, I would say, is that getting vorticity and circulation budgets in observed storms, it's a lot harder to do in observed storms than in simulated storms. And that's because of getting buoyancy observations in heavy precipitation. Remote sensing techniques don't work. Really hard to get UAVs in these areas. It's logistically challenging. There are FAA rules you got to worry about. We've attached temperature probes to balloons. We can track these by the dozens and even 100 or more now, but it's still really hard to get stuff in there. There's also a lot of reason to be skeptical of some of the past numerical simulations. So some of you in the room are aware of some of the microphysics gory details and how those simulations were set up. I'll just say that some of those probably enhanced baroclinic zones, so that might have overestimated potentially the role of horizontal temperature gradients. The vast majority of prior simulations also used what's called a free slip lower boundary condition. And then some more modern simulations are now using the semi-slip condition, which for those of you who don't know what that means, it's formulated as such. Basically, the stress at the surface is a function of a drag coefficient and the velocity squared, and you parameterize that in terms of the wind just above the surface. But there's there are assumptions that go into this as well that might be questionable in the application of that condition to a supercell simulation where you've got tremendous horizontal heterogeneity within the storm, a lot of unsteadiness, et cetera. Another omission, which this also I'd say falls kind of beyond the scope of what I want to get bogged down into today, but we use large eddy simulations we use that approach typically in severe storms modeling, and in some simulations, it's unclear whether we're meeting the conditions required of LES, especially in the environment. If you look at this simulation, the white contours, which are hard to see, this is the reflectivity field of the storm. This is a supercell. The red colors are the updraft regions. In the cool outflow of the storm, toward the rear, it's obviously quite turbulent. But if you look at the eastern part of this domain, there's no turbulence at all. It's laminar as heck. And is that a problem or not? And it just never occurred to me that this would be a big deal. But it turns out that it might very well be a big deal, and that's what leads to today's programming. So what I'm going to be talking about is an extension of this 2020 article. The 2020 article is what's the intrinsic predictability of tornadic supercell storms. I actually gave a seminar on this work at RAL, I think 2 or 3 years ago. Jared Lee helped set it up. And that paper didn't focus on how the storms were making tornadoes. I had no reason to believe that the storms weren't making tornadoes for all the same reasons I just summarized in the last 10 minutes. I was really just focused on the predictability. Here's a zoom in of what the tornadic region looks like in one of these supercells. The gray shading's the hook echo, so it's coiled up nicely. The blue contours are vertical velocity isotachs, so there's an intense updraft in here. And the tornado is where all these red isovorts are packed together. And just to preempt any potential nitpicking down the road, in the severe storms community, a lot of people get really upset if you use the word tornado in a simulation like this because they say, well, you're not really fully resolving the tornado. You don't have this thing called the corner flow region where the streamlines turn straight upward at a 90-degree angle. You really should call this a tornado-like vortex, or TLV. Since we're all among friends here, I'll occasionally say TLV for tornado-like vortex. At other times, I'll just say tornado. And just know that if I say tornado, I confess, it might be debatable whether it's really a tornado, but it's close enough. It's the model's attempt to make a tornado. All right, well, when I took a closer look at this simulation, and it kind of happened by accident late last fall, what I instead found, to my surprise, and I wasn't looking for this, I really wish it hadn't been found in some respects, because as Rich mentioned, I just took over as the department head, and a new research initiative is the last thing I need right now on my plate. I'm just trying to keep the lights on in the department. I really don't want to embark on a whole new research thread, but such is life. what happens in the simulation just wasn't what I was expecting. So that's what I'll talk about next. So just to recap what I did in this predictability study, I start with this environment. So there's a lot of CAPE, a lot of wind shear, and I do a 12-hour-long pre-simulation. I put in random temperature perturbations that triggers turbulence, and I let things just simmer for 12 hours. And you can see early on, this is a 12-hour animation of the vertical velocity. Early on, there are linear structures that form, and they're transient, they go away, and we're left with this vertical velocity field. So it's your typical run-of-the-mill boundary layer. After 12 hours of simulation, this is what the new wind profile looks like. Might be a little small from where you're seated, but we end up with a longer hodograph. It's more curved. The length and the curvature is because there's surface drag. So the drag draws the surface wind towards zero because you're losing momentum to the surface. The presence of some Coriolis causes the hodograph to get curved like this. So for those of you who study tornadoes, you'd recognize that this is a really favorable environment for tornadoes. There's something called the significant tornado parameter that's used by forecasters. When that's greater than about 1, we get excited. In this case, it's over 6. So this is a really tornado-friendly environment. And what I did was, this is just one boundary layer realization. I used 5 different combinations of random number seeds. I shifted the warm bubble around. I should say, after I run this 12-hour simulation, I drop in a warm bubble to trigger the storm. So it's an artificial initiation mechanism, deliberately artificial because I wanted to have control over the initiation process. One of the worst predictability killers in severe storms is the initiation problem. And I wanted to take that off the table. So that was by design, to have an idealized initiation. But I shifted around to the domain where I would drop that warm bubble. So I cranked out 25 ensemble members. Each environment is statistically identical. If you take planar averages of the velocity components and temperature and water vapor, it's the exact same mean sounding, exact same mean hodograph. They all make supercells. These are the 25 simulations. The white swaths that come out of these are the tornado tracks. So they all make tornadoes, but some make stronger tornadoes than others. This Storm 9 that I've boxed makes an EF3 tornado. Some of the other cases barely make any tornado. So the point of this paper was to show that essentially the details of tornado formation are virtually unpredictable. The supercell itself is quite predictable, but predicting the timing and intensity of the vortex formation, it essentially comes down to how the storm interacts with coherent turbulent structures in the boundary layer, and it's essentially unpredictable. So what I did was I took a closer look at this Storm 9. That's the strongest tornado in the case. I just picked it because it was the strongest one. I could have picked another one. And in fact, I've looked at some of the other cases. It doesn't change what I'm going to talk about for the rest of today's presentation. But Storm 9 makes a pretty strong tornado. There was another member, Storm 3, it also made an EF3 tornado. But some of these only got up to EF0 intensity. You got a whole distribution of tornado intensities. All right, so let's look at Storm 9 in closer detail. This is worth pointing out. There's no indication that this Storm 9 is special relative to the other 24 ensemble members. It's just the storm that made the strongest TLV. What's animated here is the vertical vorticity field at 7.5 meters. That's my lowest grid level for horizontal wind components. The blue line is it's essentially an outflow boundary proxy. And the black contours are vertical velocity isotachs roughly 500 meters above the ground. And reflectivity is animated over here on the right. So what we can see is right about now, that's the model tornado or tornado-like vortex. So I know this is animating rather quickly. I'll slow it down in just a moment, but see these longitudinal bands First off, we're moving here with the storm. So the storm has a movement toward the east. These bands are actually not moving east to west. They're moving basically, they're aligned with the low-level wind. They're longitudinal, streamwise velocity streaks, but velocity streaks, alternating bands of fast and slow speed, of course. This is all well known to the boundary layer community. They're going to be associated with vertical vorticity anomalies as well. They look like they're moving from right to left simply because the storm's moving from left to right. We're viewing this in the storm's reference frame. But the storm updraft's moving over these things, and one of them actually grows into become the eventual TLV. So here I've slowed it down. I've plotted only some select contours just to make the visibility a bit better. This amber colored contour, this is the 3 meter per second vertical velocity isotac at about 500 meters. So it's just showing you the updraft region. The white contours are just positive vertical vorticity anomalies. There'll be green ones as well that are negative anomalies. They're not quite as numerous, and that's ultimately because there's Coriolis in this simulation, so the positive anomalies end up being more numerous and higher amplitude, and then the gust fronts in blue. So as we move this along, notice that there are these swaths of positive vertical vorticity in the environment. And when I say environment, I mean on the warm side of the gust front. Environment is on the warm side, rain-cooled outflow is on the left side of the blue line. So the outflow doesn't have these things. These are confined to the inflow. And they move along, and it's this one right here that, if we track it, it ends up becoming the eventual tornado-like vortex. And if you're wondering, how did this go from the warm side of the gust front to the cool side? It looks like it jumped it or went through it. I'll answer that later because that's a curious question as well. And then there's your tornado. And at this point, it looks like a classic textbook case. You've got a tornado with an occluded gust front structure. It's surrounded by outflow and downdraft. If you just took a snapshot of this, you'd have no reason to think that anything weird had happened here. All right, and let's go to the next slide. All right, so for the rest of the presentation, which is, I realize we've chewed up about half the allotted time, which is fine. These are some of the questions I'd like to take a stab at. Some of these you might already be asking yourself. So where do these streaks come from? The streaks in vertical vorticity, that is. How does this tornado end up on the cool side of the gust front if it originates from anomalies in vertical vorticity that are on the warm side of the gust front? Where's the air coming from? Does it matter whether we look at the early incipient or developing tornado versus the mature tornado? Where's the circulation come from? Is it, if we do a budget of the source of circulation or angular momentum, does it come from temperature gradients? Does it come from friction? Does it come from something else? And then how do we reconcile any of this with what our existing understanding is, which I began this talk with a review of. So let's start with the first question. Where do these streaks come from? And what's their impact on, say, vortex-line? So here's we're zoomed in on a 4x4 kilometer postage stamp in the environment. The ground relative winds are in gray, so they're out of the south-southeast. It's a typical Great Plains supercell environment. South-southeasterly winds. Brown is where the flow is faster. Green is where it's slower. So these are the well-known surface layer streaks. And the presence of those velocity gradients implies that there are, well, first off, this is the vertical velocity field, so there's up and down motions here as well. But there's also vertical vorticity implied. So where you have a corridor of fast flow just east of a corridor of slower southerly flow, you have positive zeta, and then negative zeta on the east flank of a streak of relatively fast velocity. If we take a vertical cross-section through one of these positive, negative zeta anomalies, and there's positive and negative W here as well. This is what that cross-section looks like. So the shading here is zeta, the vertical vorticity component. So that's red. Red is positive zeta, blue negative zeta. The black lines are vortex lines in this plane, and the gray lines are streamlines. So you can see that we have these eddies. I guess people in the turbulence community would call these turbulent coherent structures, or just eddies for short. Here's one, there's another one down here, another one over here. These are aligned with the flow roughly, so they're in and out of the cross-section. And what they end up doing is causing these vortex lines to have corrugations in them, so up and down wiggles, let's say. So this is a much more realistic looking environment than, say, the environment we've been using to simulate storms over the years, where we typically regard the environment in a simulation, or even in a theoretical study, we take the environment to have no horizontal variability, which implies that there's no vertical vorticity, there's no W in the environment. But in real life, if you include the turbulence in the environment, the vortex lines have these corrugations on them. This is what's called lambda 2. Some of you might be familiar with this. I suspect most of you probably are not. It's a very popular thing to plot in some of the engineering fields when they're trying to identify turbulent eddies. Lambda 2, it's called lambda 2 because it's a bit of a mouthful. It's the second largest eigenvalue of the sum of the squares of the rate of strain and rotation tensors. And it's negative if you're in a vortex core. So you can, for those of you who have used the Okubo-Weiss number to identify vortices before, this is kind of like a 3D extension of that. But what we see if viewed from above, and there's a storm in here, it's just buried by all of these coherent structures. This is the reflectivity field of the forward flank up at the very top edge. There's a hook echo over here where I'm moving the cursor. But we see all these streaks in the inflow. They're obviously eddies all over the place. But what their effect is on the vortex lines, this is just another view of, it's a fairer view, it's a 3D view of kind of the 2D planar view I showed before, is that these vortex lines have these ripples on them, and then this overlying storm updraft that passes over them attaches to one of these, or many of them, and tugs upward on them. And it turns out that this is where the initial TLV amplification occurs. How it gets to the cool side of the gust front's another question. But these are actually well known to the people who study boundary layers, both in the atmosphere as well as in engineering applications. We're basically looking at the legs of what are known as hairpin vortices. And I'm not going to get into the gory details of or reviewing all we know about hairpin vortices. There's quite an extensive literature on the topic. But these are just some images I've grabbed from some of the more highly cited works on the topic. And what struck me is that, especially this figure here, this is from Davidson's textbook. He shows a vortex tube getting pinched upward by counter-rotating streamwise rolls in the surface layer. So this is exactly what I've got in my storm simulations. If you look at these vortex lines, they're pinched upward near the ground. These are the corrugations I was referencing before. They're kind of like maybe a snag in a sweater. And then just like we can, maybe this isn't the best fluids analog, but just like you can have a snag in a sweater that quickly can be tugged on and exploited, it's almost like something like that's happening in these simulations. Morris.
Hey, how are these similar or not similar to horizontal convective rolls?
So the question from Morris Weissman was, how are these similar or dissimilar from horizontal convective rolls? So these are, kinematically, they're much shallower. So a horizontal convective roll, its vertical scale is the whole boundary layer. These are confined to the surface layer. The depth is about 100 meters or so. And then they can get lifted away from the surface and break. You get this hairpin at the end. The hairpin may or may not show up in my lambda 2 field, but these long legs most certainly show up. Yeah. A lot of the figures you see in the literature are at much lower Reynolds numbers than what we've got in the atmosphere. That could be playing a role in how often we see these more idealized hairpins in these sorts of simulations versus my own atmospheric one. But yeah, we can talk more about that later. That's a really good question, though. All right, so how's this TLV end up on the cold side of the gust front? What feeds the air early versus later? Where's the circulation come from? So we need trajectories to answer all these questions. So what I'm showing here these are trajectories, by the way, that are computed at model runtime. So I'm using the full model output to get the trajectory, CM1. That's a really nice feature of it. And the colors here are just trajectory altitudes, nothing more. And what we see if we just tag parcels that end up going through the storm's low-level mesocyclone, some come from the precipitation on the forward flank of the storm, so they have outflow, cool air, negative buoyancy origins. Others come from the environment. So there's a mix. But if we look at some of the details here, and just look at the parcels feeding the developing vertical vorticity maximum right next to the surface, the story is a little different. So these are parcels feeding the developing tornado-like vortex during what I'm calling loosely the axisymmetrization period. And what I'm referring to there is the fact that the initial development of the TLV starts as typically shear vorticity. So there's a wind shift line, there's a vertical vorticity maximum, but you don't have closed streamlines, you don't have a drop in pressure encircled by closed streamlines. And somehow in the tornadogenesis process, you've got to go from that to closed streamlines and a pressure drop, and then other feedbacks can take place. The pressure drop causes air to flow inward. That amplifies the vorticity, dropping the pressure further, and there you have it. But this axisymmetrization period, this is very early. It's the very first steps in tornado formation. The parcels feeding the vertical vorticity max, these are all from the warm side of the gust front. Then as genesis proceeds, once we've now got closed streamlines and a low pressure anomaly, now we start sucking in air from the cool side of the gust front. So there's two sources now at this later time. And if we go later still, now we've got a tornado, and we'll call this the young TLV period. It's also sucking in air from all directions. And that's maybe not a surprise. Once you've got an established intense vertical vortex, it's pretty much agnostic about where the air comes from. Everything's coming in and turning straight upward in the tornado. And if I showed you this later on in the tornado's life, you'd see the same thing. So the early stages from the warm side, and then once you've got a pressure drop, then it starts drawing in air from both the cool side and the warm side. All right, so how does it get from the warm side to the cool side of the gust front? So the colored contours here are potential temperature. So the gust front is right in here where I'm moving the cursor. The vertical vorticity contours are in white. This is the 0.02 contour. And by the way, this was a near tornado formation, but it failed. It almost succeeded, but failed. If you're wondering, isn't that what we should be focusing on? It's not the one that becomes the tornado. Keep your eye on this one instead. So now we've got 0.04 with that innermost vertical vorticity contour, now 0.06. By the way, traditionally 0.01, 10 to the minus 2 per second, that's typically what we think of in the old-fashioned times of what defines a supercell mesocyclone. So 0.06 is quite significant, actually. This is 600 times bigger than F. And look at right here. So here it's still on the warm side, and now it migrates to the cool side of the gust front. And by this time, we now basically have closed streamlines, although the streamlines aren't plotted. There's a pressure drop in here, and this thing is well on its way to becoming a tornado. And it's kind of in its classic position, tucked away in the cool side of the gust front with the cool air encircling it. All right, well, if we look at this inner region and plot the subgrid scale turbulence tendency contribution, what that shows, the negative contours here are where the model subgrid scale turbulence scheme is causing the temperature to drop. So this would be turbulent mixing causing the temperature to drop. And I think there are some positive contours centered over, maybe just a little left of the vortex. So the takeaway here is that the subgrid scale term is causing the gust front in this location here to actually bleed eastward a bit. If we look at the subgrid scale contribution to the vertical vorticity tendency, this is a little harder to see, but there's a positive contour just west of the vortex center, a negative contour just east of the center. So there'd be propagation of the zeta max westward. So the takeaway here is that it's the subgrid scale turbulence scheme that's allowing this amplifying vertical vorticity max to bleed through the gust front to the cool side so that it ends up in its traditional location. And it's both the subgrid scale forcing for potential temperature as well as the subgrid scale momentum mixing, which shows up in the vertical vorticity tendency. So the gust front's bleeding eastward a bit, the vorticity max is bleeding westward a bit. All right, one other series of images I wanted to share is what the vortex lines are doing. We looked at vortex lines in one of the first slides. Hopefully you remember what Helmholtz said about how vortex lines behave. So what I'm going to show here is a vortex line through a parcel of air. You could say it's a cherry-picked parcel. I would say it's just one of many, but it's representative of a parcel that's approaching the developing tornado. I'm going to show you this parcel as it moves toward the developing tornado and the vortex line drawn through that parcel. So I find the parcel and then I draw the vortex line through it in both directions as far as I can take it until it hits a boundary or goes somewhere where I don't really care what's going on, and then I truncate it. It's tempting to think as I animate these, or don't animate them, I reveal the other times, that this is the same vortex line at each of these times. Strictly speaking, it's not really, because Helmholtz's theorem is that the vortex lines are material lines if and only if there's no baroclinity and it's inviscid flow. This is not inviscid flow. The baroclinity is pretty negligible here, but this is not really inviscid flow. So strictly speaking, this isn't the same vortex line in each panel, but I'm going to say close enough. I'm asking for maybe a bit of a reprieve on that. I don't think that the evolution of the vortex lines is going to be wildly different than if we look at this one particular line or set of lines through this one particular parcel. So the story that it tells, if you look at this vortex line here, see how it has the little wiggles? And over time, this, by the way, the updraft isosurfaces are these gray and kind of pear-shaped isosurfaces. They tug the vortex line upward. And then look at this 58-80 second time. The vortex line almost is making a complete right turn straight up. If we look a little later, same thing, this thing's going straight up. And in fact, the tilting and stretching terms in the vertical vorticity equation at the location of this parcel are quite large. So this is, the tilting term is about 41 times 10 to the minus 4. Stretching is about 27. You add that up, you're approaching 10 to the minus 2 per second squared. That's enormous. That'll take you from 0.01 to tornado strength in seconds. These are extreme values in this parcel that's coming from the environmental side of the gust front. And that's how the vortex line goes from this to this very quickly. All right, what about the wall cloud? You might be wondering, well, we see wall clouds. Doesn't that mean parcels must be coming from the cool side? So the short answer is yes, there is a wall cloud. It doesn't lack a wall cloud. Here's an isosurface of the cloud. There's the wall cloud. It's maybe some storm chasers have seen lower hanging clouds. This one hangs down about 300 meters below the ambient cloud base. If I look at trajectories into the wall cloud, indeed they come from the cool side of the gust front, as they must. This is rain-cooled air, it's humidified, a bit cooler, so it has a lower LCL. But if we look at where zeta max actually is, that's where the red shading is, this is what becomes the incipient tornado-like vortex. It's actually slightly offset by a few hundred meters from the lowest part of the cloud lowering, and the trajectories into this are coming from the environment. So what I would argue is that the parcels feeding the wall cloud, they indeed come from where they're supposed to, but the developing zeta max at cloud base, it's slightly displaced from the lowest cloud base lowering, and I would argue that if this subtlety were to be found in a real storm, there's almost no chance we'd be able to detect it. We'd need the very best photogrammetry overlaid with the very best dual Doppler analysis. I don't think we'd detect this actually if this difference was manifest in a real storm. All right, what about circulation origins? And given the hour of the day, it's closing in on beer o'clock, at least in Eastern time zone. I'm not going to get into the gory details of how we do these material circuit analyses, but the pioneer in the room is sitting right up here, so you can ask Rich all about it tomorrow morning. But this is a really valuable tool, I'd say powerful tool, for splitting up the various sources of circulation that ultimately can be converged to make a tornado and obtain very large vertical vorticity values. So essentially what you do is you track a whole lot of parcels that make up a circuit. There are literally millions of parcels in this circuit, and you'll see it come into the storm, it's flying in here, and it's going to collapse upon the developing vortex. And the budgets are what they tell us in this particular case, without getting too deep into the weeds, is that early on, the circulation that gets used to make the tornado, it actually is coming from the environment. This C0 refers to the fact that it's in the initial circulation of the circuit when the circuit's way out in the far field, nowhere near the storm. If we look later and do a similar analysis, things are a little different actually. This blue line, and I know there are a lot more lines, I could spend 15 minutes explaining every aspect of this figure, so some of you will just have to take this as on a leap of faith. But this blue line is an indication that later on in the simulation, the subgrid scale term ends up being an important source of circulation. What that really translates as here is it's coming through the lower boundary condition. So there's drag at the surface. What ends up happening is as the tornado matures, inflow gets accelerated, and that acceleration generates additional horizontal vorticity. The horizontal vorticity very near the ground is really a function of just the ground relative wind speed at anemometer level. So as those speeds pick up, you end up picking up more horizontal vorticity, and that ends up getting reoriented into a place where it can contribute to the tornado's angular momentum. So returning to what we started with, which was this conceptual model, which I had been feeling pretty good about for a few years, is this is just not really what I'm seeing in this Storm 9 ensemble member, unfortunately. What I'm actually seeing is something that looks more like this. Vortex-line, which has wiggles on it in the environment, gets drawn upward. And one thing I haven't talked about yet is the fact that the storm relative winds are basically aligned with these vortex lines. And the term for that is streamwise horizontal vorticity. The horizontal vorticity in the environment is extremely streamwise. That ends up being a really favorable aspect of the storm environment, because what ends up happening is that when these vortex lines get lofted upward, you end up getting the vertical component of vorticity co-located with updraft, which leads to the vertical vorticity being able to take advantage of large stretching. So it gets very quickly amplified, and it really doesn't even matter whether you tug on the negative foot of one of these corrugations or the positive foot. It all gets yanked upward, and it all ends up becoming vertical, positive or cyclonic vertical vorticity owing to the tilting effect. And these little wiggles, of course, come from these turbulent coherent structures due to the same surface physics that's been well known in the boundary layer community for decades. You get vertical vorticity on the order of 0.04 per second, as low as 7 meters out here in the environment, which these are not negligible values. And as best I can tell, there's no evidence in this storm, at least, that baroclinic generation is significant. It just doesn't show up in the circulation budgets. Later on, though, in the storm, there are indications that surface drag adds a boost to the circulation. So if you zoom in on where this red circle is, this is my best attempt to kind of show that the winds accelerate a bit just above the ground as the storm matures. All right, you might be wondering, what role does the gust front play, if any? Does that help somehow tilt these environmental vortex lines or allow the storm to better exploit the corrugations of the vortex lines? So I ran a simulation. I'll call this the no-cool simulation. So there's hydrometeors, but I don't let them cool the air. So there is some negative buoyancy just due to the hydrometeor mass, but it's confined to the rain shafts. There's no cool air emanating as outflow from where the rain is. So there's no evaporation. There's no melting and sublimation. There is melting and sublimation, but they're not allowed to cool the air. They're basically snipped in the temperature tendency equation. So the answers appear to be unclear to the first question and no to the second question. So here's the movie. Storm 9 is on the left. That's the one we've just been analyzing. And the no-cool simulation's on the right. So the first thing you notice on the right is that there's no gust front, and that's to be expected. I'm not allowing the hydrometeors to have latent cooling effects. And this still makes a heck of a tornado. Makes almost a 50 meter per second EF2 tornado, despite the fact that there's no gust front and there's no outflow in any traditional sense. So that's kind of interesting. I also wanted to run a simulation like the late 20th century style simulations that we built all of this understanding on. I mentioned a lot of this pioneering work was done here inside the halls of NCAR. Is there something weird about my environment here that's giving me a different picture than the story that had been told in previous decades? Or can I recover the 20th century story if I rerun my simulation configured like that 20th century style simulation? So I use a free slip lower boundary. I have no turbulence in the environment, so it's a laminar, horizontally homogeneous environmental boundary layer. Do we get a tornado forming the standard way in the review at the beginning of the presentation? We'll call that the standard baroclinic mechanism. And if so, then where does that mechanism vanish to when we include turbulence? Like, why would it just go away? So the answers to those questions, the first is yes, I actually do get the 20th century understanding if I rerun the simulation, the 20th century configuration, which in a way that's a relief. On the other hand, now there's more explaining to do, because then it leads to the next question. Well, then where the heck does this baroclinic mechanism disappear to? So here's the C20, the 20th century simulation on the right, shown again beside the Storm 9 simulation that we've been analyzing. So notice it's very laminar in the environment. There's no vertical vorticity in the environment. And we get a TLV in the classic position on the immediate cool site. There it is right there, and then it eventually shoots out to the west. But this looks just like the simulations of past decades upon which so much of our fundamental understanding is built. All right, and if we look at trajectories into that C20 storm, on the left we have the early trajectories. They come exclusively from the cool side of the gust front. This looks just like that simulation I showed at the very beginning from Johannes Dahl. Parcels coming straight out of the north. They descend, come along the ground, and then erupt into the developing tornado. And then later on is on the right. Once we establish a tornado, now we're pulling air in from everywhere. Some parcels come from the environment, and we're still drawing air from the cool side of the gust front. All right, let me skip to the circulation budget. So what we see here, I did the same sort of material circuit analysis And voila, the baroclinic term dominates. So this is exactly, if this was the only simulation I had run, I would have said, all right, this forms the good old-fashioned way, check, yep, nothing unusual here. But this is completely different than what we're seeing in Storm 9. Yeah, this is the Rotuno and Klemp 85. This might be the most heavily cited paper in the history of severe storms. Is it? It must be. Maybe Weissman and Klemp 82. Should have an arm wrestling match. Okay. And then I wish Hugh Morrison could see this. Maybe he wouldn't want to see this. The cold pools are very different between the C20 storm on the left and Storm 9. The blue shading is the cold pool strength, basically. Much stronger cold pool in the C20 case. This is the exact same microphysics scheme. Exact same environment. The only thing different is the environment on the right has turbulent structures in the environment, and somehow in an exotic way that I don't have a conceptual model for, it really alters how the microphysics scheme performs. Yikes. And we've always been told, the importance of baroclinicity in supercells is to enhance the horizontal vorticity in the forward flank. Well, here in the C20 simulation on the left, bingo. Orange is where there's enhanced horizontal vorticity just on the cool side of the gust front, which is in white. Looks very classic, looks exactly like what we've always imagined. But in Storm 9, the horizontal vorticity in the forward flank is actually weaker than in the environment. And the reason is that this is where the slowest ground relative winds are. So as I mentioned before, horizontal vorticity next to the ground is a function of ground relative wind speed. And depending on the ground relative hodograph, certainly in this Storm 9 case, you've got southerly winds. As those parcels enter the cold pool, they decelerate a bit before turning left and coming back down into the mesocyclone. Their ground relative wind speed drops dramatically, and they end up having a lot less horizontal vorticity near the ground as a result. All right, I think what I will do next is you're the first group to see this stuff. I didn't have a strong sense for how verbose I would be. So I'm going to cut to the end, and then we can open up for questions. And then depending on where the questions go, maybe you'll see some of the other goodies. So it would seem that at least one of the following has to be true. Either the prior simulations that used a laminar, horizontally homogeneous environmental boundary layer developed tornado-like vortices for the wrong reasons. That's one possibility. Or my simulations all developed them for the wrong reasons. The third possibility, this is maybe the most generous, is that supercell tornadoes form in a wide range of ways in the real atmosphere. And our simulations realism is now increasing a bit, and we're finally capturing the broader diversity of ways that you can make a tornado. The good news is that the things we currently use to forecast tornadoes, strong low-level shear, low LCL heights, that would still work even if the dynamics in play in Storm 9 are what is more like real life. I am going to jump to this. Yeah, I just mentioned this. So yeah, low LCL, strong low-level shear. This is kind of state-of-the-art for what the Storm Prediction Center uses to discriminate tornado from non-tornadic supercell environments. High LCLs tend to favor strong cold pools. That's disruptive in simulations that are set up like C20, but it would also be disruptive in my Storm 9 simulation. So that's good, right? And if what I found would flip the forecasting methods upside down, my findings, I think, would have almost no credibility because our ways of forecasting storms work pretty well. So if what we're doing works pretty well, it can't be all that far off. But it would work for the scenario shown in the Storm 9 simulation as well. And it all comes down to how strong that environmental low-level shear is. If that's weak, you can't tug on those vortex lines regardless of whether or not they have corrugations on them. If these vertical vorticity streaks actually facilitate tornado formation and aren't just passive nodes for where tornado formation first forms, or where tornadoes first occur. There might be some additional things forecasters could look for. They'd want to be looking for things that favor these coherent structures. So stronger ground relative wind speeds would be one. You wouldn't want the surface heat flux to be too positive either. And in fact, storm chasers know that you tend to not get tornadoes when the surface heat flux is very large. Nobody's really given a great explanation for that. Maybe Andrew Crook did many years ago. He had a hypothesis maybe along these lines, actually. But there's something called 6 o'clock magic. That's kind of when the surface heat flux passes through zero. It seems to be a magical time for storms. And coincidentally, 20 years ago, I wrote an article, and I didn't really understand or believe the results, but one of the best discriminators between tornado and non-tornado producing supercells was just how fast the wind was blowing at the surface. Faster was better. But I didn't really understand it then. Maybe that's tied to this, or maybe it's just a coincidence. And then regardless of the answer to this provocative statement, it would seem that one of the following must be true. At the very least, we need to understand why the microphysics schemes are operating so differently. I mean, this is a different question even than the broader, never-ending question of how do we make the microphysics schemes better. Here, like a side trip on that is, are we validating these schemes or testing these schemes with the right types of simulations? I don't know the answer to that. And that's not really my wheelhouse either. So I don't even want to speculate anymore on that. And then ways of what we're doing at the lower boundary is going to be really important as well, to the extent that getting the turbulence right near the surface is so critical to these little details in the vortex lines. We better darn well do a better job of representing what's going on near the ground. And there's a whole LAS sub-community that spent their entire career on improving LAS near walls. And that's a whole nother series of talks. So I'm not going to say anything more about that. And then additional processes, I'm really reluctant to say that my Storm 9 simulation is the simulation or the best simulation. Yes, it has the realism of the environmental turbulence, but it doesn't have a surface heat flux. It doesn't have cloud shading. Maybe when the anvil spreads out over the environment, it tamps down the turbulence. So yeah, there are a lot of uncertainties. I definitely am not in a position where I'm going to stand up here and say my Storm 9 is superior to the 20th century simulation. It could be that aspects of both are right. So, and then the last point I'll make here is that we really need also volumetric buoyancy observations. I mean, I've been saying this for 20-something years. Because if we're going to validate which storms have the most realistic cold pools, we got to get the observations there. And these are really hard to get, particularly above the ground. And we need them not just at the surface, but volumetrically, especially if we're tracking trajectories in 3D and we want to do anything like a real life material circuit analysis. We need to know the buoyancy along that whole path. And we're trying to do this now at Penn State in my group. Other groups are trying stuff now too. Some groups are using UAVs. That's tricky to get volumetric data with just a couple of UAVs. You'd really, yeah, you need a whole army of UAVs. We're flying lots of balloons. This is an animation actually of about 75 small balloons. So they're not traditional weather balloons. They're just this big, and they get sucked through the storm, kind of like Twister. But we didn't have Helen Hunt or Bill Paxton with us. But that's all I'm going to say for now. Thanks for your time and stamina. That was very long. I realize that.
Questions on the Slido. So from George Bryan. Hi, Paul. I'm trying to reconcile your results with Chris Nowatarski's PhD work. Didn't he find that boundary rolls aligned perpendicular to the supercell motion were relatively bad for near-surface vorticity generation? Could you comment on how your results compare with his? Thanks.
Thanks, George. This slide is for you. This is one of the ones that I skipped. Yeah, so I had a whole deck here of reconciling. There's at least 5 or 6 things that need to be answered. So yeah, there's the Nowatarski simulation. I guess one thing I'd say about that simulation is delta X was 200 meters, so he lacked TLVs. So I probably can't I'm reluctant to make an apples to apples comparison with that simulation. And the HCRs there, that's a different beast than these surface layer structures. So I think the safest answer I can give you is I don't really know yet, and I haven't really thought about it enough to answer that question probably at the level you're hoping I can. Yeah, I think that's all I'll say. Thanks.
Next question from Sean Mertzik. Interesting talk. It looks like the cold pool of your simulations is less turbulent than the environment, at least in terms of vorticity maxima near the surface.
Yep.
What is the opposite, which is the opposite of past simulations? Is this what we would expect, or is turbulence underdone in the cold pool in your simulations?
No, that's a good question, Sean. Hi, by the way. My take on that, I mean, I haven't done the turbulence, the TKE budget analysis, but I would assume that the stratification in the cold pool here is damping the turbulence there a bit, and the surface wind speeds are weaker there, ground relative speeds. So there's less shear generation of turbulence, and there's also stratification.
Okay, and third question from Brian Green. Hi, Paul. Really interesting work. Your results seem to highlight an important reliance on SGS performance, which, to my understanding, can be quite dissipative near the surface. Could you comment on this challenge with interpreting your results? Thank you.
Subgrid scale, yeah. Yeah, that is who asked that? Brian? Brian, yeah, that's a really good question. So, yeah, you're absolutely right about the traditional LES just blindly applied to any simulation like this being too dissipative near the surface. Basically, the problem is that the eddies get under-resolved as you approach the ground, and it ends up causing one of the principal assumptions in LES to be violated, which is that the largest eddies are well resolved. So there's some other details there, but the end of it is that the subgrid scale model is not doing what it's supposed to be doing, and you end up getting excessively strong shears potentially near the surface. And there's a whole long list of people in multiple communities, from engineering to the atmosphere, that have spent a large chunk of their life trying to come up with workarounds for that. Some are here in this building, in fact. That's one thing I'm working on. I mentioned Ying Pan's been a collaborator of mine in recent years. This is what we've been working on, actually, is adopting some of the engineering strategies. Something called a two-layer model is one thing we've been exploring, and it's more flexible, basically, than the off-the-shelf semi-slip condition that's just taped together with LES in kind of the industry standard way of doing severe storm simulations now.
Okay, questions from the room.
So you touched on this on your last couple slides, but I've been wondering about this. Would it be hard to take your simulation and put in radiation effects to kind of tease out how these fluxes and anvil shading may affect the turbulent structures?
That would be very easy, I think. The harder part might be doing a full 3D radiation where you get the slant angle right. I think I did this. I messed in this world a long time ago. When I was a grad student, I used some Oklahoma mesonet data to look at anvil shading effects on storm environments. And then one of my grad students in the early 2000s, Jeff Frame, this was his PhD work. And if I remember right, it was tough to do the MPI with the 3D slant angle, but I feel like we had a workaround that. This was 15, 18 years ago. I can't remember the details, I'm sorry, and even if I could remember them, I'm sure there are probably better ways to do things now than the way we did things. Yeah, I might just be motivated enough to try to put that in now. And the best case scenario is it makes all of these structures go away under the storm, and then we can just revert to the 20th century style understanding again.
Well, the 20th century results, the circuit analysis, does ultimately show that air has to come in, the circuit has to come from both the warm and the cold side.
Yeah.
So it is incorporating warm air eventually into the circulation.
Yeah, I mean, the circuit's broader, so yeah, the parcels actually feeding that initial zeta max are inside of the circuit. Yeah.
If you looked at a larger scale or up above the ground, above, a few hundred meters, it could be that in your storm 9 you get back to the. It's possible, I would say, that you got back to the, the original results, and it's only the very low near the surface. Is that possible, you think? Or?
I don't know. I mean, if you're only, so if we asked what air is going into the 250 meter altitude zeta max, there's definitely air coming in, even in the early stages from the environment, because the environmental parcels are coming in they're entering zeta max at 7.5 meters, and those parcels then pass through 250 on their way up. So yeah, I wouldn't think so, but. I mean, one question, a related question, and this bugged the heck out of me, is I asked the question, I realized I didn't answer it, which is, where does the baroclinic mechanism vanish to? And I think what's going on here is that once you have an established vortex, it's sucking in air from everywhere. Even tanker trucks and cows are going up, at least in the movies. But air is cold air, warm, it's all going in and up. The dynamic pressure gradient, infinity, buoyancy, 0 at that point. But long before you get to that point, where that initial zeta explosion has to occur, in this 20th century simulation, if we invent a term called available vertical vorticity, available zeta, there is no available zeta in the environment. It's only on the cool side of the gust front. So the only place that the initial eruption can occur is on the cool side of the gust front. So that's where it happens, because that's the only place it can happen.
But it does happen.
And it does happen, yes. Storm's perfectly happy making a tornado that way. It's just that we thought that was how they all happened. At least that's what I was kind of assuming. We hadn't seen any evidence to the contrary. But you put in a turbulent environment, and now all of a sudden you have available zeta on the warm side of the gust front. And in fact, it's even more available than the stuff on the cool side. We've got 0.04 at 7 meters. That's much better than what I've got on the cool side. So that's where the initial development takes off. And then again, once it's taken off and now you've got closed streamlines, bam, now you're taking in air from everywhere again. That's what my take is on this.
Great talk, Paul. You said that there's nothing special about Storm 9. But what in some of your other storms, like Storm 8 or whatever, that produced only a marginal TLV?
Yeah.
What was different there? Was the surface layer, those surface layer rolls, were they just weaker, more infrequent? Was it just kind of stochastic differences?
It's
entirely?
the latter, yeah. The rolls these environments are statistically identical. The only thing different, it's just different realizations of a turbulent boundary layer, but the statistics are identical. So yeah, it's, I have a simulation now that I'm looking at, the weakest one. I mean, the animation's the same. You see these structures getting overridden by the overlying supercell updraft as it moves along. It just doesn't, it seems to be stochastic. I mean, if I did a vorticity analysis, it would reveal the most profound finding, which is that there's more stretching in Storm 9 than in the other storm that doesn't do it. But that's not very illuminating, unfortunately. But another thing, in terms of reconciling this with past observations, so we have past observations of vortex lines that and trajectories that really emphasize the cold pull. It's not just the models, it's in the observations too. But the problem is that in observations, we're typically only observing stuff on the cool side of the gust front because that's where the scatterers are from the radar's perspective. Most of these radars in our field project aren't seeing anything on the warm side of the gust front. They're seeing very little. So we don't really know what's there, what we're missing.
Okay, I'll just add a footnote from the 1985. I thought at the time we had 1 kilometer horizontal resolution, so minimum resolve scales were several kilometers. So I thought at the time what we were explaining was the low-level mesocyclone,
Okay.
not the
Yep.
TLV.
Right, right.
And in fact, by 1985, I had done all this laboratory work where the surface friction is really critical. So I kind of knew that it wasn't going to produce a TLB. So
Yeah.
while I'm still alive, I could actually respond.
You're not going anywhere.
Yeah. Anyway, thanks again, Paul.
Thanks.